In the previous video, we discussed the concept of neuroelectromagnetism and the presence of electromagnetic sources in neurons. Now, in this video, we aim to first model neurons as electromagnetic sources. In other words, we will transition from neurophysiology to the concept of an electromagnetic source that generates action potentials. Next, we will model the arrangement of neurons and their resultant fields. Finally, we will provide a brief overview of electromagnetic modeling of brain tissues by first introducing geometric information, which we will then reconstruct and transform into a material from an electromagnetic perspective. Ultimately, we will model the brain as an electromagnetic environment that includes electromagnetic sources. A source model in the context of brain electrical activity is a mathematical formulation that characterizes the primary current density generated by neural sources within the brain as a function of both space and time. The source space is defined by all parameters of a parametric source model, effectively spanning the possible configurations of the neural activity. The instantaneous primary current density, denoted as J, R wink with tongue sticking out, where R is the spatial location and P represents the parameters of the source model, can be approximated as a vector within this source space. As the neural activity evolves over time, the primary current density J, R T wink with tongue sticking out, traces a trajectory within the source space. The electromagnetic fields generated by this time-evolving current density are described by Maxwell's equations, modified for the quasistatic approximation typically used in bioelectromagnetism. These include nabla E equals ρ/epsilon, where E is the electric field, ρ is the charge density, and epsilon is the permittivity of free space. Nabla times E equals del B/del T, relating the electric field to the time variation of the magnetic field B, nabla B equals 0, indicating the absence of magnetic monopoles, and nabla times B equals mu, J plus epsilon del E/del T, where mu is the permeability of free space and J is the primary current density. These equations govern how the current density within the brain leads to the generation of electromagnetic fields, which can be measured externally by techniques such as electroencephalography, EEG, and magnetoencephalography, MEG. The source model, therefore, serves as a crucial framework for linking the dynamic internal neuronal activity to the observable electromagnetic signals, allowing for the reconstruction and interpretation of brain dynamics from external measurements. As previously mentioned, the opening and closing of sodium and calcium pumps located in the walls of the neuronal cell create a voltage difference between the intracellular and extracellular spaces. This voltage change, in turn, triggers the opening and closing of adjacent pumps, leading to the flow of current along the axon. In the simplest case, this process can be modeled as a current dipole. As shown in the top figure, a neuron can be modeled as an electric dipole, where the flow of ionic currents across the cell membrane during action potentials creates distinct regions of positive and negative charge. This dipole moment is dynamic, varying as the action potential travels along the axon. By modeling a neuron as a dipole, one can simulate the electrical field generated by neuronal activity, which is crucial for interpreting data from electroencephalography, EEG, and magnetoencephalography, MEG, which is shown the equivalent electromagnetic model in the right side of the figure. The bottom of this slide shows the configurations of neurons and major intracellular currents. In pyramidal cells, the long, thick apical dendrite creates a preferred direction for intracellular currents, making them detectable from a distance. However, detectability depends on the cell's positioning and orientation. As shown in C, many pyramidal cells in the cortex align in parallel, allowing the far fields of their currents to add up, which can be detected by EEG or MEG. Conversely, in circular alignments like in the hippocampus, D, these fields cancel out. Additionally, symmetric neurons, as shown in B, also tend to have currents that cancel out within the cell. Configurations A and C are known as open fields, while B and D are closed fields. An extended cortical activation with variable strength and orientation of the primary current density can be modeled by electric current dipoles. A single focal source model is chosen such that it optimally approximates the sum effect of all these currents, which is demonstrated by red arrow. Alternatively, the source area might be subdivided into multiple volume elements, each represented by an electric current dipole of its own, which is called distributed source model, demonstrated by blue arrows. As shown in the right side figure, 3 different source models can applied: a distributed model, left column, where the source area is uniformly divided into small elements each described by an electric current dipole, a multiple focal model comprising 2 electric current dipoles, middle column, and a single focal model comprising 1 electric current dipole, right column. In the upper row, we see a more continuous distribution with a sharper focus at the top and a broader blob at the bottom. While the single focal model is clearly inadequate, the multiple focal model accounts quite well for the true distribution, although the broader blob is less well captured. The distributed model is a more accurate description. In the lower row, the primary current density features a single focus, which is well approximated by a single focal source. The other two models are clearly redundant. In this slide we are going to discuss the spatial distribution of the produced external fields and their relation by the orientation of the dipoles. As previously mentioned, based on the concept of the equivalent current dipole, the synchronized activation of one part of the cortex can be detected as the external field. These concepts are shown in the top side figures of this slide. In addition, their location, orientation, and their polarity will define the spatial distribution of external field. As shown in the bottom figures of the slide, tangential dipoles produce external magnetic field, but radial dipoles don't create magnetic fields. It means doesn't seen in MEG. To go deeper in the context of the spatial distribution of the external fields here in this slide, we are going to show the typical topographies of EEG and MEG on real head geometries caused by a single dipolar source positioned closely underneath the inner surface of the skull. Topside potential distribution of EEG and magnetic flux density distribution of MEG on the head surface for a tangential dipole. Positive potentials are drawn in red, negative ones in blue. The potential difference between the two contour lines is 10 microvolts. Bottom side for radial dipole. Positive flux densities, drawn in red, denote flux coming out of the head, while negative flux densities, blue, denote flux going into the head. Normally the flux difference between two contour lines is 1 picotesla. In the previous slide we concentrated on the possibilities for the generation of local membrane potential changes, which was for proximal excitatory synapses. Now in this slide we are going to demonstrate the impact of the polarity of EEG and MEG. Excitatory and inhibitory synapses create positive and negative local postsynaptic potentials, respectively. Excitatory synapses can be located distal, away from the soma, or proximal, near soma, leading to currents away or towards the cortex, PL, surface, respectively. Inhibitory synapses are mostly on or near the soma, causing intracellular currents to flow away from the PL surface. Depending on the location of the active neurons on the cortex, currents flowing away from or towards the PL surface can effectively be oriented perpendicular, on the gyral crown, or tangential, on the sulcal wall, to the head surface. Typical EEG and MEG topographies for source configurations are shown in the right side column. Another parameter that should be taken in account is the impact of the rotation. First, we are going to demonstrate the decomposition of the rotated dipole in radial and tangential form. For this purpose, in right side of the slide in figure A2 dipoles are considered by location in close proximity. Distance is almost equal to 1 cm, one on the gyral crown, which is demonstrated by red arrow, the other one on the sulcal wall in green arrow. In figure C, D the simulated EEGs for these dipoles, interpolated between 124 EEG electrodes, small green disks, and viewed from above. In B the dipoles from A are shifted to a common position without changing their orientation. Hence in figures E, F the EEG topographies are virtually the same as in C and D. Thus, the differences between the two dipoles, as observable by EEG, are rooted predominantly in the difference in dipole orientation and not in dipole location. In left side of the slide, we demonstrated the cortical currents, volume currents, and scalp topography from different directions of localized dipoles. In this figure pyramidal cells and their apical dendrites are symbolized by diamonds and thick outward bars. A subset of return current loops is depicted by arrows in light red to illustrate where they create positive and light blue where they create negative voltages. As shown in figure, depending on the net orientation of the cortical patch, the zone of maximal inflow from scalp into depth shifts from above the patch in radial, to more posterior in tangential and fully posterior in oblique. These currents create the typical 3D voltage topographies on the scalp related to the cortical convexity in radial case, in the depth of a sulcus in tangential case, and the more common case of an oblique net current involving both superficial and sulcal cortex. Dynamic source modeling is a behavior modeling approach for neurons based on feedback principles. In this model, shown in the left figure, the state variable evolves according to a differential equation and an initial condition. An output equation converts the internal state, such as the mean membrane potential, into a source model parameter like dipole strength. The Hodgkin-Huxley model, one of the most popular dynamic source models, is depicted on the right. It includes voltage-gated channels for potassium and sodium, described by nonlinear differential equations, with other currents summarized by the constant leakage conductance GL. This concludes our introduction to source modeling, with more details to follow in future videos. Space modeling is a key principle for solving neuroelectromagnetic problems. To achieve this, the head must be realistically modeled as an electromagnetic space. This slide illustrates the transformation between a realistic head and a spherical volume conductor model based on boundary value modeling. The simplest model is represented by concentric spheres, which are shown in red with fixed ratios between the radii, corresponding to the scalp, outer skull, and inner skull surfaces. Alternatively, the head can be modeled using concentric ellipsoids, which are piecewise homogeneous and isotropic or radial/tangential anisotropic. These are fitted to the upper part of the tessellated scalp surface, which are shown in green contour extracted from MRI data. To map a point from the real head volume to the spherical model volume or vice versa, a beam from the origin through the original point, characterized by the spherical angles theta and alpha, is considered, and the intersection ratios with the respective head surfaces are computed. This method allows for the transformation of both source and electrode positions, with electrode positions corresponding to an orthogonal projection onto the surface of the fitted sphere. The field approximation and mathematical treatment for these models is achieved through a quasi-analytic solution using spherical harmonic expansion of the electric potential. Each material in the electromagnetic model is characterized by its permittivity, permeability, and conductivity. The table provides details on the domains, their boundaries, and the corresponding electric and magnetic properties. To develop an accurate volume conductor model, the boundary element method, BEM, is a widely used approach. As illustrated in the slide, the process begins by loading and reading anatomical data, such as MRI scans. The MRI images are then resliced to ensure that the voxels are isotropic, meaning they have the same dimensions in all directions. This reslicing step is crucial for simplifying the subsequent segmentation process. Next, the MRI data is segmented to differentiate various compartments, including the scalp, skull, and brain. Following segmentation, a triangulated surface mesh is created for the BEM. This method involves defining several boundaries for each tissue type, such as the scalp, outer and inner skull surfaces, cerebrospinal fluid, CSF, and brain tissues, including both gray and white matter. The triangulated surfaces effectively describe these boundaries, and each compartment is treated as homogeneous and isotropic. The finite element method, FEM, is a crucial technique for creating electromagnetic space models of the human head, particularly for neuroelectromagnetic source reconstruction problems. Similar to the boundary element method, we start by acquiring and pre-processing anatomical data, such as MRI or CT scans, followed by the segmentation of different tissues. Next, we generate a finite element mesh, either tetrahedral or hexahedral, that balances detail with computational efficiency. This slide presents two FEM models of the human head with multiple tissue segmentations and varying levels of detail, emphasizing the role of different mesh types in accurately representing anatomical structures. In FEM, accurately assigning material electromagnetic properties and defining boundary conditions are essential. This concludes our presentation. In the next video, we'll delve into the application of FEM in solving forward problems and explore the specific uses of various mesh types.